All right, folks, it's back in action here. In this video, we are going to go through using DeMoivre's theorem to find both powers and complex roots. So example 3 is going to be how to find powers, and example 4 is going to be finding complex roots. Now, a first very important thing about using DeMoivre's theorem is that whether you're finding powers or finding complex roots, the complex number that you are working with must be in polar form. So if the problem starts off, if the number you're given originally is in rectangular form, it must be converted first. And if you don't remember how to convert, go back to the previous video where I go through examples of how to convert a complex number from rectangular form to polar form. The next thing is that then we're going to have two formulas. Okay, there's a formula for finding powers and there's a formula for finding roots. Now, the formulas are not nearly as complicated as they look. I'm going to go through how to do both of them, but probably one of the most common errors that students have is they mix this up in what their answer is supposed to look like. When you are asked to find a power, meaning you're going to raise something to a power, you will only have a single answer. You'll have one answer, okay? It'll come down to a single number or a single complex number. That's it, okay? When you are finding roots, you will always have multiple answers, okay? Because you're finding multiple roots. So keep that in mind. I can't ask you to find complex roots and you give me a single answer. You will have to have as many roots as I ask you to find. Now, let's go through and just understand quickly what it is that finding a power means, all right? So let's say I have this complex number, radical 3 minus I, and I want you to raise that power, raise that complex number to the 6th power. Algebraically, so before this course, before DeMoivre's theorem, what raising something to the 6th power means is to multiply it by itself 6 times. And you're going to need to pause this to write all this down. And then what you would do is you would FOIL each of these. So you would most likely, from your Algebra 2 days, you would group these, and of course they're all the same. So you would group them and you would do this first and you would FOIL those and we'd get a 3. Then this is a negative radical 3i, but this is also a negative radical 3i. So that gives us a negative 2i radical 3. And then that product is a plus I squared. But of course, I squared is a negative 1. So then we would clean that up. And this becomes this, which becomes this. Now, remember we had that product 3 times, so now I'm going to have this result 3 times. So this one became this one became this, and this one became this, okay? Then we would need to keep foiling again, and we would pick any 2 I chose, just because I was doing it first, that I have a reason why I like it, but it's just a preference. Then I'm going to FOIL this out. So again, I just FOILed. I FOILed each, my first outside, my inside last, okay? And that got me to here. Again, I squared is negative 1. So then when I clean all of this up, that gets me, so now I have a negative 12 in my 4. That's where that negative 8's coming from. So this cleans up to this. I still have that other binomial, so it comes down, and then I need to FOIL this last one. And when I FOIL the last one and I expand the whole thing out, it's getting pretty messy. This gets me a negative 1 again. I clean everything up, and now I can see that these 2 middle terms are actually going to drop out. So I have a negative 16 minus 48. So my final answer is a negative 64. So we did all that work just to get to that negative 64. Now, I think you guys would all admit that this is a lot of work, and there are tons of places in there that we could have made a mistake. On top of that, a 6th power isn't really even that many. If I had made it a 10 or a 14, this would become so cumbersome, we would definitely not want to do it. DeMoivre's theorem is going to allow us to do this computation very, very quickly. So let's go through how the DeMoivre's theorem would work on this problem. First, remember, DeMoivre's theorem requires that our complex number be in its polar form. So we would quick find our r value. So we'd have our square root of our 3 plus 1. That's going to give us a 2. Then we would quick do our tangent theta, and we would do our -1 over our radical 3. We would remind ourselves that our point, our original complex number, was in the 4th quadrant. So we would write our theta value. And our theta value, we could write it in degrees, or we could write it in radian form. It doesn't make any difference at all. So I'm going to go ahead and write that as 330. Okay. Or 11 pi over 6. So when I write this in polar form, I could write 2 cis 330, or I could write 2 cis 11 pi. There we go. Sorry, kind of messed that one up there a little bit there. 11, there we go. 11 pi over 6. Either one of those is fine. Now, to apply DeMoivre's theorem, since we've got it in our polar form, DeMoivre's theorem, I have it written up here, says that we're going to take the r value, r2, and we're going to raise it to whatever power it was that we were asked to find. So up here on the very beginning, if you look up there, it says find that power to the 6th. So I'm going to take 2 to the 6th power. Then I'm going to take that 6 and I'm going to multiply it by whatever angle that I found in its polar form. So in this case, that radian number is going to be a lot easier to work with. So that's now going to give me 11 pi. So then when I put that into the formula, it becomes 2 to the 6th was 64. So it becomes 64 cis 11 pi. And then they will always take out all of our extra rotations. So we want to take out all those extra rotations and get it down to the smallest positive coterminal angle. So this would become 64 cis pi. And if you expanded that out, what you would find, and again, you could go back to the previous video if you're not sure how to do that. If you expanded this out, this will in fact simplify to a nice 64. So if it asked for it in rectangular form, you would expand it and simplify. If it asked for you to stop in polar form, you would have stopped right here. Again, recognizing that you need to get this angle down to its smallest positive coterminal angle. Now, that's 7 minutes on just raising something to a power, and now we're going to go the other direction and we're going to do roots. Remember, roots will always have multiple answers. If you give me a single answer when I ask you to find complex roots, there's no way your answer is complete. Okay. Now, DeMoivre's theorem on the roots also requires that our number be in its polar form. So what we want to do is we want to find the 4 complex roots of the number 1. And that question definitely sounds pretty crazy. So the number I'm working with is 1. I want to write that in a complex form, which means it has a real portion and it does not have an imaginary portion. So this is my rectangular form of that complex number. Now I want to get that into polar form. So my r value is the square root of 1 plus 0, or 1. If I plot that point 1, 0, it's right here. I could certainly go through the tangent exercise of doing 0 over 1, but either way, I'm going to get a theta value of 0. So now I have an r value and a theta value. That's going to give me a polar number of 1 cis 0. Now, when I plug that into my formula says that I'm going to do the nth root of the r value. So I'm doing the 4th root of 1. It won't always be 1 or be this simple, but that of course is just 1. That one's not too bad. And then I'm going to take my theta value of 0. I'm going to divide it by 4 because that's the number of roots I want. I'm going to add to that. I can either use 360 or I could use 2 pi. I'm going to divide that by 4. And then, of course, I'm going to have my k. So my formula is going to look like 1 cis 0 plus pi over 2k. Now, when I go to expand that, just like we've done before, I'm going to have a k equals 0, a k equals 1, a k equals 2, and a k equals 3. I'm going to have to do as many k's to get me up to 4 roots. So that's going to get me to a 1 cis 0, a 1 cis pi over 2, a 1 cis pi, and a 1 cis 3 pi over 2. Now, if you expand all of those out, okay, we go through the whole expansion exercise just like we did in the previous video. If you expand those, this will become a 1, this will become an I, this will become a -1, and this will become a -I. So if it asked for your answer in rectangular form, you would give me that. If it only asked you to find the complex roots in polar form, we could have stopped right here. Now, the last thing that I want to show you is how that answer actually makes any sense. So over here in the other column, we're going to look at an algebraic example of what it asked us to do. It wanted us to find the fourth roots, all the fourth roots of the number 1. So if we wanted to solve this problem algebraically, this one actually is really simple. We would raise both sides to the fourth power, so become x to the fourth equals 1. Then we would move everything over to the left side and set it equal to 0. Then we would factor the difference of squares. We could then solve each of these. Then x squared minus 1 would, of course, give us an x equals a plus or minus 1. And the x squared plus 1 would give us a plus or minus I from our algebra days. So we can see that our answers algebraically are the same as what we get when we use DeMoivre's theorem. And this one, again, it's much easier. This one happens to be much easier in the algebraic form. But again, I want to emphasize, if this was a more complicated number or the number of roots was bigger, this algebra would become much too cumbersome for us to do. So just to reiterate, roots always have multiple answers. You need as many answers as roots it asks you to find, and you must have your problem in polar form first. So if they give you a problem that is either a pure imaginary or a real number, you need to write it in this form even before you start these steps. Now, this is a pretty complicated process, so you definitely want to spend some time reflecting on this and then also really working through all the practice problems that we're going to do.